right, welcome back. Again, this is track 1, implementations and use cases beyond mobile. Our first presentation this afternoon is meeting demands for camera and sensor interfaces in IoT and automotive applications. Man who's going to be responsible for keeping you awake after lunch is Hezi Saar of Synopsys. Hezi's a staff product marketing manager at Synopsys and is responsible for its DesignWare HDMI, mobile storage, and MIPI IP product lines. In addition, Hezi co-chairs MIPI's marketing steering group, and he sits on the MIPI Alliance Board of Directors. He brings more than 20 years of experience in the semiconductor and electronics industry and embedded systems. Hezi, thank you.
Thank you very much.
Yep.
Hi, everybody. Oh, we are all awake. Good. So let's start. We'd like to talk now. I'm going to start. Yeah. Okay, so we'll start. Hopefully the sessions in the morning were interesting to you. Hopefully this one will also be very interesting to you. Actually, I was listening to most of the sessions, and they were mostly focused about automotive, and although my slides also talk about automotive, I'll try not to focus on automotive, just to bring a little bit more perspective on some other applications where MIPI specs are being used. So this is really the agenda for today's talk. We'll, of course, start with the implementation of MIPI specs in mobile, but then we'll transition and show some examples of how MIPI specifications can be used in applications beyond that. So we'll talk about it now. After that, we'll go and provide some quick overview of MIPI specs that we'll be discussing, like CSI2, DSI, D-PHY, and I3C. We see a wide adoption of these protocols in beyond mobile kind of applications, so we'll be talking about that. And we'll end with SoC consideration. So what do you do with this kind of information when you go and design your SoC? And we'll summarize, of course, at the end. So as been discussed before, MIPI display and camera interfaces are used widely in mobile. So every smartphone today uses MIPI specification. They are optimized for mobile applications. They provide the best way to transfer camera and display information from the display or from the camera to the SoC. Today we're seeing more and more cameras and more displays are being used in a single mobile terminal. And we continue to see the wide adoption of those specs in mobile. But where are we going from here? This is really MIPI Alliance strategy. And building on the success in the mobile terminal, which is mostly smartphones, that's really where MIPI specs are proven in terms of meeting low power demand, meaning performance requirements, meaning the optimized nature of a mobile terminal requirement. In addition to that, meeting EMI consideration, meaning the channels that are widely used in mobile. It's not just PCB, it's beyond that. You have flex cables, you have chip on glass. So channel is not an easy task to solve. But building on the high volume and low cost, if the implementation that we see for MIPI specs in the past several years, we're now seeing adoption of MIPI specs trickling into other applications. I'll be talking about them. One of them is automotive, another one IoT, wearables, and virtual reality, augmented reality, mixed reality kind of applications. Okay, let's start with IoT. So I think this wasn't discussed in depth, but we are starting to see different applications which can be called IoT, Internet of Things. This is an example of point of sales IC that's been designed in order to solve the specific needs of point of sale. So for this one, for example, we're starting to see MIPI camera and MIPI display being used. We're also seeing sensors. So MIPI I3C is starting to be adopted in this kind of applications. Beyond MIPI specifications, which are entering into that segment, we also have other interface IP requirements like DDR, mobile storage, ADC, Bluetooth, USB. But in addition to that, embedded vision, processor, security, and sensor fusion, since you are communicating with different sensors. So of course, this is only one IoT application. There are many more. But just to show that this kind of block diagram illustrates MIPI usefulness in this kind of application. Going forward, we are seeing ADAS being the #1 application driving electronic adoption in automotive. Of course, there are more applications, but ADAS is the one that we're seeing the biggest growth today. So we've been dividing that into two segments. One of them is the passive driver assistance system, which really provides information to the driver that they can act upon. The second category of ADAS systems is active. So actually allowing the car itself not just to provide information to the driver, but actually to act upon it. So really applying the brakes if there is an event that requires braking. So ADAS is one step towards the autonomous car, but this is really what we see today in the electronic market. And this is one example of a hot application in automotive. I think Lindley talked about surround view. So this is exactly what the implementation that it is. I think also Toshiba also discussed that a little bit. So really what we're seeing in this kind of system is different camera modules that are deployed in different locations in the car. In this example, it's actually 4 locations of the car: front, back, left, and right. And for each one of them, you have a different module that is responsible in capturing the image and transmitting it to the main processor to process the information and either provide that indication to the driver or apply or provide the active action itself. In each one of these camera modules, you would find a CSA2 image sensor. You'll find also an image signal processor that receives the signal and processes it. And you'll find some kind of bridge, so a transmitter to LVDS or Ethernet, something like that, that will enable the camera module to communicate reliably the information across very, very long channel. In addition to this, we are seeing the infotainment processing unit deploying MIPI DSI. There's some additional display interfaces that are being deployed in automotive. I think it's a transition phase where MIPI DSI is starting to see deployment, and I don't think it's going to be too long before we see MIPI DSI being adopted widely. These are just two typical automotive SoCs. On the left-hand side, this is the high-end ADAS SoC, and see multiple kind of interfaces are required to support that. LPDDR, Ethernet, HDMI, PCIe, SATA, ADC, embedded vision, security, sensor fusion are all needed. But on the MIPI side, we're talking about MIPI DSI, multiple MIPI CSI2 interfaces, MIPI I3C, again, connecting to many, many sensors, and MIPI SoundWire for the audio. I have to mention that for automotive application, I think you heard that from previous speakers, automotive applications have different requirements than mobile. It requires functional safety, ISO 262. It also requires AEC Q100 testing for the SoC side. It requires quality management support by the vendors. So there's slew of requirements by the SoCs which are different than mobile. And IP providers, for example, work towards that. And the infotainment system, which is a chip which is located separately, this is more of an SoC that will be processing the multimedia kind of information. So it's more like a tablet kind of application. So it requires also multimedia interfaces. Similarly, on the MIPI side, it's DSI, CSI, I3C SoundWire. But on the other interfaces, USB, DDR, Ethernet, HDMI, PCIe, SATA. And something which requires mentioning is that today infotainment systems use eMMC. Sometimes they use SD card. We're starting to see transition towards UFS. So UFS is built on MIPI DevCon and MIPI UniPro specifications. And the JEDEC UFS is utilizing this specification, and providing this kind of storage interface into automotive is really where we are starting to see the UFS standards go. The last segment I would like to touch on is augmented and virtual reality. We see a lot of use cases come forward today which require this kind of SoCs and implementation to be used. This is some of the images here are showing mostly in enterprise use cases, which this is our perspective. This is first where we see this kind of technology being deployed first. So helping in maintenance, home maintenance, for example, maintaining engines, or more on our professional side, medical, providing information in real time, and this is more on the business side, providing this kind of information as mixed reality to the user so they can increase their productivity. This is a teardown that was done by iFixit, which shows HTC Vive teardown. I'm not inventing anything here, just showing the kind of components that today are used in the HTC Vive. I think different chips are used here. I think new designs will use different approaches. What I wanted to mention is that similar to what the Toshiba speaker discussed, there's a Toshiba chip over there which converts HDMI to dual MIPI DSI converter. So this is, as a comment, it's also found on the Oculus virtual reality system. So we are seeing this kind of mobile specification that are used widely in smartphones. MIPI specs are now starting to see themselves in virtual reality. Some of the examples of the new cases, so on the top left, you can see high-end multimedia processor, very similar to what we see in the Vive, for example, but typically today it has multiple components. We're starting to see SoCs deploying multiple DSI and CSI inputs and having DSI and CSI outputs as well. So you're receiving multiple information on the surrounding of the user, receiving the DSI output from a standard application processor, augmenting all of those realities into one single image, and sending that out to the display itself. So the user itself can see this kind of mixed mode reality when they look out. We're also seeing I3C for sensors as being deployed in this kind of systems. We also see some kind of applications which require gesture recognition, and typically these use two inputs from cameras that capture depth and capture movement of the individual, then merging them together after some kind of processing, transmitting that on a single CSI2 stream to the external application processor. And lastly, this is a bridge kind of implementation. Until those kind of implementations in virtual reality is going to be robust, there are a lot of requirements for bridging. So receiving one display standard, which is a standard output of, let's say, a computer or computer-like SoC, and splitting that to the two eyes, the left eye and the right eye, so you can actually see it properly. There was a release by Microsoft a few weeks ago. Actually, they revealed their HoloLens processing unit, HPU, what they call it. So it's a processor which is packaged with LPDDR, with an Intel processor, all of that as a processing unit, allowing this kind of capability to the end user. What we can take out of it, and this for you users or future users of MIPI specs, is that MIPI interfaces are used, and they're actually located here per the die. So the HoloLens processing unit uses 5 camera interfaces. And you can see that they're deployed at the bottom right. And compared to the entire SoC and the other components, you can see that MIPI interfaces are small in size, low cost in the implementation. You can actually have as much as 5 camera interfaces, which consume very little in terms of die. Okay. Just looking at time, I'm okay, I guess. We'll want to move forward now and talk about the MIPI specs that are typically used in this kind of multimedia applications, and we'll go over them in slightly details. First of all, let's touch on a popular MIPI CSI2 interface. So typically, the most popular implementation of CSI2 or camera interface in MIPI is CSI2 over D-PHY. And in this kind of interface, you have the host and you have the device. The device is typically the image sensor itself that captures the image, like you can see here in the frame buffer, and then puts it together and transmits it chip to chip to the other side. The host is really the application processor that receives the image and actually receives it in and then can process it further. So really what it means that when an image is being captured, the frame buffer inside the image sensor itself captures that and then provides that packet or provide that information to the CSI2 transmitter. So a packet needs to be built. So this kind of line of the image itself needs to be built properly. And the packet builder, really what it does, it adds the required information such as virtual channel identification, data format definition, so what is the data of the CSI2 that was captured, the payload byte size, and the ECC. So the ECC itself is protecting the header itself, so just to make sure the information that captured there is in. But then you have actually the image itself. When it is transmitted, that line is transmitted, we added CRC to it. So that's how a packet is being built, is being fabricated, you can say, in the packet builder, and then transmitted to the lane distribution of the D-PHY. And that's really where you can actually see that where the D-PHY is distributing the data between the different D-PHY high-speed lanes. So in this example, we're showing it's being distributed into 2 D-PHY lanes and being transmitted to the other side. And on the other side, you can actually extract the packet that was packed from the transmitter, being sent to the packet decoder itself that actually takes that information, associate the virtual channel with whatever needs to be associated with. That's how you get that line to the other side. So that's really how the frame buffer is being transferred from the device to the host. What this chart really wants to communicate, it shows the CSI2 packets and the type of packets that are being used. But really what it means that CSI2, using the camera workgroup specialty, has been working closely with a PHY workgroup in the MIPI Alliance to come up with the most optimized way to transmit camera data information from one side to the other. So short packets, for example, were defined and are used for synchronization. Frame synchronization, allowing you to do the most out of the protocol. And image data itself is really used in a long packet. So that's really where the data is being transmitted. And then what the MIPI spec allows you is to switch to low power mode, a low power state between those packets if you want to, or stay in high-speed mode if you really you care about latency. And this is how virtual channels are being transmitted. You can see that in this example, you have virtual channel 0, virtual channel 1, and there are different lines associated with those imagers, and they're being transmitted one by one like that to the other side. So effectively, one CSI2 implementation can actually capture multiple virtual channels. In this example, what we want to talk about here is MIPI DSI over MIPI D-PHY. And then this one is DSI video example. So DSI has multiple modes. There's a command mode. There's a video mode. This one we'll talk about more on the video mode. Typically in command mode, just to give you a quick overview, Command mode is we assume there is a frame buffer in the display driver itself, so it can capture the image, and the host itself transmit the data through commands actually to the other side to make the changes in the video stream itself. And what we can see here in the DSI video example, very similar to the camera side. Again, the display work group worked closely with a PHY work group in order to come up with the most optimized protocol to transmit the data most efficiently and allow power reduction. So synchronization events such as VSync and HSync are transmitted using short packets. In this example, we're showing the VSync signal being transferred to the packet builder, and that information has been built into a short packet, being transmitted to the lane distribution, and being transmitted via 2 high-speed burst lanes to the other side, where you can actually extract the VSync information and get that. The second one is actually HSync, and we can see it here. So different synchronization events that are happening. And again, in HSync, you can actually put that in the short packet and transmit it to the other side via the mechanism that is allowing you that with the D-PHY. But really, the payload itself is really the valid image line itself. So that's being transmitted with a packet builder. It's being put together in a long packet with a header, with ECC, with CRC for the entire packet, and being transmitted out through the lane distribution to the DSI receiver side. So this is how an image from one side, from the transmitter side, is being generated and actually sent to the other side. For both of those examples, we can say that the most popular physical layer that is being used in the MIPI Alliance is the MIPI D-PHY. Of course, the other physical layers that are available that can do that. The MIPI D-PHY is providing you a mechanism to really provide the data in the most efficient way. It actually have a single clock lane and multiple data lanes, so the clock is separate from the data. It's not embedded in the data. It's different than other SerDes technologies, providing a synchronous forwarded clock to the other side, which actually simplify things, right? You do not need to recover the clock. The system itself does not need to be as sophisticated. You have ability to provide DSKU information. We have additional low power and high end modes, and high speed modes, which allowing the two sides to exchange information in the most efficient way. There's no encoding, so there's no overhead. So the data itself is transmitted on the data lane and actually matched with the clock. In the new specification for D-PHY 2.0, there's spread spectrum clocking. So that's really supported to reduce EMI or take that into consideration in very high speed modes. And probably lastly, the fact that we heard that MIPI D-PHY and MIPI CSI2 and DSI are used in examples in automotive and IoT and other virtual reality kind of applications is because MIPI Alliance and the MIPI specs are used in high volume mobile applications. Cost is going down. Multiple designs, multiple architectures, all of them are optimized again and again to meet the needs from those applications. So proven in millions of phones, proven in large ecosystem is one of key requirements and key considerations that you take into account when you decide which interface to use. And also, D-PHY is not standing still. We just wanted to show you the latest D-PHY matrix and the specification. So over here you see the RX D-PHY specification version. Over here you see the TX. You see the speed. So D-PHY 2.0, for example, goes up to 4.5 gig, but it's backwards compatible with D-PHY 1.2, 1.1, and 1.0. There's some other consideration you need to take into account, but in general, the success of MIPI D-PHY is because it continues to be backwards compatible and take that into consideration. So new specs really augment the existing ecosystem. They do not really replace it. You can really benefit from the wide adoption of MIPI CSI2 and DSI devices that are available here. Okay, wanted to touch a little bit about I3C since multimedia kind of applications starting to utilize that. So just in high level, I3C is expected to standardize sensor interfaces, which typically today use I2C or multiple I2C interfaces, and SPI for bandwidth. So really I3C is supposed to take the best of both worlds. So combining standard two-line connection, but putting all the interrupts in band. So this is really to allow you to reduce the additional pins that are used for interrupts with I2C. Secondly, it can get you to fast speeds. So typically SPI, for example, would be used to get to the faster speeds where a sensor needs to transmit more data. Now, sensor capture more data as we go in. There are more sensors in phones. I think Lindley showed about a dozen sensors used in phones right now. So we see the same thing in phones and in other applications, many, many sensors. So really standardizing everything into a two-wire bus will actually simplify everything for integration going forward. So one bus where I3C master can connect to I3C slaves, to I2C slaves, some legacy kind of implementation, and also to I3C secondary master. This is the encompassing architecture of I3C. And we see three main examples of I3C use cases. One of them, and probably the most popular one, is Sensor Hub, where the SoC itself communicates to a sensor hub itself that collects all the other information and aggregates that together and provides that to the SoC itself. We see a sensor subsystem is where the I3C master connects to multiple sensors. And the bottom one, which I'll touch about that later, is image sensor. We talked about MIPI CSI2. MIPI CSI2, as you probably know, use a CCI, camera control interface. It's a two-wire I2C-like interface that connects image sensors to application processors. Image sensors use widely, as you know, with connecting to application processors. So it's just natural for image sensors to move and transition to I3C. And connecting that will actually allow image sensors to be connected on the same sensor bus as everybody else. I want to touch on the sensor hub. So effectively what it does is really offloads the application processor from collecting and aggregating the sensor information. Actually, all of that can be done by the sensor hub itself, which is located here, is configured as a secondary master in the system. And that it means it collects all the information. So as soon as the secondary master has the relevant sensor data information available on the I3C bus, it can then communicate to the main master, wakes it up, the main application processor, and transfer that information. This is the most efficient way in terms of total system power, if you look at it from that angle, to make a more efficient system deployment. We talked about image sensors, so we're starting to see more and more image sensors adopting I3C to be connected to the same I3C sensor bus and displacing CCI. And this is really the long-term vision. If it is possible or not, time will tell. But since the image sensor can connect through I3C, one futuristic use case may be to have the image sensor connecting and starting to send pixels over I3C bus directly to the host processor. Now, the bandwidth is limited, but if you are looking into some kind of application that needs to track certain movement, then multiple image sensors located in the surroundings of a human being or any machine will allow to provide some kind of information or valuable information to the host processor. So we're talking about a very cheap and very low cost image sensors, and this kind of use case or use cases will come to the market, we believe, in the next couple of years. Okay, so this is where we are. I have about 30 minutes, right? So about 10 minutes to go. So let's talk about design considerations. Right, what do you do with the information I just provide you? I mean, you have that information already. If you're a MIPI member, you can access the spec. You can talk to different IP vendors and get that information. But when you put the requirement for your next design in, what do you take into consideration? First of all, the bandwidth required application or applications you're going after. What is the D-PHY or physical layer version and speed that you want? The number of ports, the number of lanes for each one of them. You determine the optimal mix of ports that you would want to have in your SoC, and then you can add it up. But I just wanted to show you one example. Of course, it's much more complex than that. But you can, for example, in this example, I'm just changing one parameter, which is the D-PHY speed or D-PHY version. So if you have a D-PHY, if you pick the CSI2 transmitter or the device controller connecting to a transmitter D-PHY version 1.1, which runs up to 1.5 gigabit per second per the spec, you can connect to transmit that data to the RX side, so receive the image information up to 1.5 gig per lane. But you can make one parameter change, and instead of version 1.1, you can target version 1.2, which gets you up to 2.5 gigabit per second. It changes the dynamic, it changes the area, it changes the power consumption, it changes the number of lanes that can be used. It provides you future-proof and more power efficient, more area efficient capabilities in your SoC. But all of the other parameters that I mentioned before also needs to be taken into account, such as configuration and interrupts and how you want to manage that, memory usage, all of that. These are the parameters that you need to take into consideration when you integrate CSI2 in your system. I want to touch and give you one additional example. Of course, we have many more examples about design consideration, but this is one of them. So typically we have, well, not say typically, we have customers that would like to go after different applications. They cannot really afford having SoCs or multiple SoCs going after application A, B, C, D, and Z. And they want to have the most efficient way to reduce the cost, reduce the design, reduce the mask, reduce everything, the manufacturing cost. And they would like to have the same SoC targeting two applications. I'm showing you a very simplistic way of doing that. In one application that SoC is targeting, they envision to want two separate connection to CSI2 cameras. Each one of them can carry up to 2 lanes. So in this kind of example, you have a 2-lane D-PHY connecting to the CSI2 host controller, and another 2-lane D-PHY connecting to the other one. So simple 2 streams. But they want to have that on power up, for example. The same system acts differently. The 2-lane D-PHY act like a 4-lane D-PHY, and instead of connecting to 2 separate streams, they want to connect to a single stream. All of that is possible with the right design consideration ahead of time, and that can be done on power up. So very efficient way of implementing things and allowing you to reuse effectively the real estate that you have and you saved for that and actually capturing multiple applications. So talking about application processor going after multiple markets, we say mobile, automotive, IoT, augmented reality. So how do they do that? With some kind of flexibility in the ports and assignments of the ports, all of that is possible with the right planning. And one more thing, because we talked about channels, so I wanted to reference that as well. So today in the D-PHY spec, there are 3 reference channels that are supported. Short reference channel, standard reference channel, which will be mostly smartphone kind of channel, and the last one, which is the long reference channel. This is already part of the spec, and it's part of what D-PHY supports. So just to make sure you're all on the same page, it's not just for D-PHY, it's all the MIPI C-PHY, D-PHY, and M-PHY. All of them support all the 3 reference channels. But there's a misconception in the market that MIPI specifications can be used only in smartphones. Well, that's not true. They're used mostly in smartphone, or they're used in every smartphone. But even in smartphones themselves, the PCBs are not simple. You have flex cable, you have chip on glass, you have some rough areas, you have radios. So all this kind of noise immunity and channel or noisy channel are supported by the MIPI specs. And the last one is you can see that MIPI specs are also entering longer channels. Now, we're not talking about meters yet. This is something MIPI Alliance is still striving to analyze and to support going forward. But we're not talking about very short distance. That's what I wanted to say. Okay, so effectively, this is really summarizing things. When you are looking into integrating CSI, DSI, D-PHY, I3C, all of these kind of interfaces, looking into complete production-proven and interoperable solutions, MIPI Alliance provides that information, that solution to you, and you can actually adopt that risk-free. So in summary, representing Synopsys here. So we are a provider of multiple interface IP, but in the MIPI one, we make a lot of investment. And specifically on this topic, we're talking about CSI, DSI, D-PHY, and I3C. These are leveraged in mobile and beyond mobile right now. We are seeing wide adoption beyond the traditional customers we have in mobile. Some of that is already public on our website. Some of that is not. IoT, automotive, augmented reality, virtual reality, all of these are right now deploying it. They already have silicon. They're already in production. We provide complete camera, display, and sensor interface IP for designers to use. And we enable, using this kind of interface, we enable new set of applications in automotive, AR, VR, and IoT markets. Really, if you want, you are looking for a low-risk integration, low-risk adoption, you can use production-proven IP from Synopsys. So really, reducing your cost, your power for multiple instantiation is really what we talked about. Testability, we do not want to ignore that, right? The IP itself can support low-cost testability in production and in debug. So we can talk about that too. One last thing, we have our booth, as you probably went and saw that, but want to highlight one thing. We are showing UFS solution connecting to our customer silicon, actually, which is in production in phones right now. UFS is in phone, as you know. Second one is CSI2. Third one is actually pretty unique. It's actually the industry first MIPI I3C demo. So we have our I3C controller running and connecting to a device. So please come and see that. So if you have questions, we're here to help you. Thank you. Any questions? Don't be shy.
Any questions for Hezi?
Yeah, there's a question here.
I'll just give you a mic here. Thanks.
So in the DSI command mode display, is the TE signal a part of the MIPI spec? And what does it do? Is it similar to the VSync or what's? I feel like the spec doesn't have it the document doesn't describe it very well. So
Talk about the tearing effect?
Yeah.
Yeah, we should probably take it offline.
Okay.
Yes.
Hi, I have a very general question. So earlier you were talking about for the IoT, the I3C is the interface. So, but is there any competing interface or technologies that people are also looking into besides I3C for IoT space?
Okay, from the customers that we talk to, and this is really why I can give you that kind of information. They mostly use I2C and SPI. There's some proprietary interfaces out there, which I did not dig into, but I mostly see I2C and SPI, and I do not see any competing standard right now. We actually see fairly wide adoption, starting with the host side, to use and to adopt I3C. We already have few customers using I3C, so we see that momentum building up. But I think I3C is a slam dunk from the way I see it. If everybody can standardize on a two-wire interface and it can really fulfill the standardization of a two-wire bus and the bandwidth, it's probably the best thing since sliced bread, I think.
Any other question?
Cool. Thank you very
Thank
much.
you. Thank you, Hezi.